Okay, we are live streaming. Almost. Did everybody get some sleep at least? A little bit of sleep?
I'm back. So I think most of us are already online. So we start our lessons now.
Great.
I'd like to share the screen. And so, hi everyone. Can you turn on the speaker? Yeah. Okay. So today we are going to talk about how to generate meeting code based on the model you created yesterday, and also teach you some meeting fundamentals, the logic behind the code. So first of all, we have to distinguish different techniques for making fibers into fabric. Like I just gave 3 examples, but there are more. Knitting belongs to the very first one, that it has a loop fiber structure. So the loops are interlocked with each other to form the whole fabric. And in comparison with that is fabric made of weaving and braiding technique. They have different organization of the fiber structure. And for knitting, there are many type of machine to make knitted fabric, like weft knitting machine, warp knitting machine. The difference between them, that weft knitting machine can use one single yarn to form the whole fabric. So you can see it's a continuous yarn and then move to the next row. But for warp knitting, each warp use an individual yarn. So multiple yarns are knitted together and interlocked with each other. And here in this workshop, we are using weft knitting machine and especially flat knitting machine. Flat knitting machine has the flat needle bed. It's different from the circular knitting machine, and it has much more flexibility in knitting variations in shapes and also structure variations. And circular knitting machine now often used for mass production of flat clothes, but not with irregular shapes. And here's one example of the most simple toy knitting machine. So this is an abstraction of the automatic ones. Here you can see a very flat knitting bed. So needles are plugged in this needle bag. And here the rectangle one is a carriage. So it moves from right to left. And under the carriage, there are channels to control the movement of the needles. And here's a upgraded version. It has 2 needle beds, a V bed, and also we can see a computer control panel here. So the only manual work is to push the carriage from left to right, but it can automatically select needles and also do pattern variation with bigger efficiency. And this is an automatic one, so the needle selection, also the movement of the carriage are automatic, and there are also some other installations add onto the machine to make sure the manufacture process is fully automatic and secure enough. And here is a video, short video shows how the carriage move on. And there's triangle panel under this carriage. So by the movement from left to right, right to left, it actually moves the needle upward and downward. So this shows a process how a knit is formed. Like this is a yarn that is newly fed. By moving the needles upward, it can open its mouth and the yarns are fed into the hook on the top, and then the needles will go downwards, and its top can close its hook, so the loops can be formed and interlocked with each other. There's also some short videos showing, maybe give you a very primitive image of how each knit are formed. And here shows a single needle. So a fabric, a knitted fabric is made of repetitive units. We call it a stitch or a knit, and those stitches are interlocked with each other, and the whole fabric has a basic structure of wheel and courses. And then if we want to, I would like to introduce, this is interface of the software for the automatic knitting machine. It's actually like a bitmap drawing, and you can see that actually each pixel represents a knit here. So the major task for us, especially for architecture design, is that how to translate 3D geometry or pattern variations into these pixel drawings. So we know exactly which knit is located where. There are many techniques to translate 3D geometry into knitting patterns. Here are some very common ones. Oh, sorry. Like this one, it's through geometric analysis, then we add cut lines onto the surface and then flatten them. And according to this flattened pattern, we can create the knitting pattern. And here is also another one with similar approach, but this kind of method is limited to very, how to say, symmetrical geometry, and for those non-standard and arbitrary geometry, it is really hard to give them accurate geometrical definition. So in architecture field, some architects have already developed their own technique, like this one by the group of from Royal Danish Academy of Fine Arts. They use kangaroo tool to flatten this stretched fabric onto the 2D plan and then translate it into pixel fibers by using the relaxation function of the kangaroo. And also Mariana Popescu from ETH, she developed a 3D a method that can automatically generate knitting pattern from 3D meshes. This is an early paper. I think she did a lot of improvement on this method, but the one presented in this early paper, it incorporates two different techniques like increase and short rows. So the pattern she created is like this. It doesn't, so I will talk this later. So for this method, you can see it doesn't have a very continuous knitting path that from the beginning to the end. So there are some ending points here, but she did some improvement later, but it's not shown in the paper yet. And we will introduce that later. And also from the computer graphics, people have developed things like using primitives like those triangle and tubes and short rows. They create arbitrary geometries, but those arbitrary, but the working process of this method is not like we input arbitrary geometry then to generate its knitting code. It's rather to define those primitives first and then adjust them and to fit the target geometry. So what architects really want is just to input arbitrary geometry because we don't know the topology of those so like this one, the robot one, if you want to knit this shape, you have first determine what topology or what combination of this primitive, how to use tubes and short rows, how to combine them, and what's the parameter we use to repeat short rows or step how many tubes here. So we don't have a, if we are not very familiar with knitting, maybe it's really hard for us to determine how many primitives and how do they combine together to get a geometry that we want. So later, Narayana also provide a very powerful tool that it can automatically transfer any input geometry into knitting codes and to the machine G code. And if you are interested, you can find articles. Here's a reference. And but for us, maybe just knitting shape is not enough. Architects would like to add structure performance analysis or other design aspects onto the surface of this geometry. So, but this method directly transfer geometry into the very low level machine action command. So it is kind of hard for us to add more things into this very complex system. So we are still searching for a simple way that has a very close connection to the software that architects use, and also easy for us to incorporate our like fiber variations and other design aspects onto this 3D geometry. So here, back to how to knit this 3D geometry, the key challenge. I would like to introduce some thoughts from my own research. So to knit from the craft, in term of the knitting craft, to knit the 3D geometry, you have many ways. I just list these three of them. First, you can knit it flat, and then by sewing them following specific sewing lines, you can achieve 3D geometry. And also you can use partial knitting or increase or decrease to create 3D geometry. The difference between these two is that the second one doesn't have to sew a lot. So you further eliminate the handwork part. And the third one is tubular knitting. So for partial knitting, the geometry is only limited to the surface. Tubular knitting can knit tubes, but this one may have higher requirement on the knitting machine. And sometimes if you want to knit tubes, complex tubes like have several branches, it may require a very high-end automatic machine. So for me, partial knitting and the second choice is more universal to us, and I chose partial knitting. So first, let me show you what is partial knitting. Partial knitting is like if this is the needle bed, for the first row, if you need a full needle bed, then the following rows you don't need the full bed. Then there will be short rows inserted in this area, and in those areas with the accumulation of these short rows, more materials are added to this area. It will become little bumps, and with designers designing the length of those short rows and also the location of short rows, we can achieve very specific geometry. So this is how short row behave. So this is in this needle bed, we have 4 needles, and next row, we just need these 2 and need this 2. And for the last row, we need a full 4 needle again. But these are connected. So we don't drop the gap. So you can imagine this is how to say exaggeration. So in fact, this loop length is the same as this one. So when it is shrinked its length to the average length, you can imagine this part has more material compared to the right part, and it will become a bump. And also, maybe you have a question like, why don't I choose increase or decrease? Increase and decrease is also like short rows. It can change its row length by transferring, like I just need 4 needles here, then the next row I want to move 5 rows, so I split one. Maybe there's something wrong with this drawing because there should be one need here. I forget to draw that. So I split this need into 2. So this the next row can be longer. And this is for tubular knitting. So you can see the yarn goes front and to the back and then to the front. So it knits like this. The shortage of increase and decrease is that because we have to split the knits here, so it can add tension to this knitting row. If we split more knits, it will become too tight for knitting. So the yarns may break or cause other damage to the needles. So in my approach, I just use partial knitting by adding short rows to achieve this 3D geometry on the surface of the fabric. So I developed, during my PhD research, I developed a brief program to translate 3D input mesh into a knitting graph, as well as 2D knitting pattern. While doing the computation, the fabric is abstracted into a grid composed of this rectangle faces as well as triangle faces. Like those triangle faces are the start or the ends of a short row. So they merge here and then so this is the short row. Here is the ordinary long knitting row. And so the task is now translated into how to compute this knit mesh given 3D geometry. While doing the computation, the only limits of this is the dimension of a knit. So we can see here the dimension of each rectangle face is actually the same with typical physical knit dimension. And also to go further, we can also have a close look at the structure of this abstracted mesh. It has parallel wheel structure, which we can take it as warps. And it also has parallel course lines, but here we can see some, so the warp lines are parallel, but the course line can join or merge into one at some point. This is the end or the start of the short row. So here give us a clue how to generate knitting pattern over 3D geometry. We first generate this evenly spaced parallel line as warps onto a 3D surface. Here I give a reference point, so all the lines are arranged in this direction. You can also give this point at other places on the geometry. And then we generate this weft lines by dividing. You can see I'm dividing the warp lines by the same length, and this is the length of a knit, and then connect those points to the closest point on the next warp lines. After that, there's how to say, knittability optimization process that can adjust the structure of this knit graph, because even though we compute this graph, but it doesn't guarantee that a continuous knitting path can go through all the knits. But this is a case for partial knitting. Let's go back to, it might be a little bit abstract. If you have any question, you can ask. So like this shows the process of partial knitting. You can see the red line. Actually, it's a continuous one line, just moving from the left to right. And next row, start from the same point, go backwards, and then stop here and go turn around and go back. And then for the last row, it starts from here and go back again. So it can be knitted through a continuous single yarn. So generating this knit graph is not enough yet. We still have to do optimization process to make sure that one single line can connect all the knits, all the faces in this knit mesh. So after optimization, we know exactly which knits are located in which place over this 3D geometry. So then we can draw them and also do analysis to them to find whatever we want according to whatever performance. And like this one here, it has at the bottom, it has higher stress. So we distribute more reinforced yarns here. The pattern becomes thicker, and for less stressed area, we have thinner reinforced patterns. And here is an example how this is mapped onto a 2D drawing, and this shows the reinforced area. So in this part, I used a different yarn, thicker than the black one. So more fibers were distributed in those reinforced area. And also give you a brief understanding of the logic behind this knitting pattern. So here's a dome, here's the knitting pattern for it. It is actually kind of similar to the approach that I mentioned by adding cutting line, like this one. You can imagine adding the cutting line here and then develop into a flat paper pattern. It has the same triangle parts, and here, but it's different that if you made it this way by sewing, it still needs sewing here, but by knitting, as I showed the short row knitting process, there are still stitches connecting those two parts. So it can automatically produce a 3D geometry instead when not needing any sewing work. So I'm not talking too much about this um, detailed code because I'm sending you some example from the Grasshopper. Maybe you can play with it and we can communicate if you have further question. I know most of you don't have the background of knitting. Maybe it's quite new to you, and also it's a little bit hard for me to express it in English accurately. So if you have any question, you can just ask and I can show you more in detail. Thank you. Okay, so I'll send you the email. Yeah. Virginia, do you have anything to add? Can you understand what I'm saying?
Yeah, I mean, well, so I'm early in my PhD research where Yiga finished hers last year. You finished yours or 2 years ago now. So I've done a lot of reading and studying of this, but I haven't done as much experience as she has. So I can understand completely what you're saying. It's very clear.
Okay.
But I think the first time I saw a lot of these patterns and was reading about how they work, I was a little confused. So it takes some time to study them and play with them, and then you can understand how they're working. So even if the students, you're confused right now, I think over the next day or so, when you really start to see this working, it will make sense. Does anyone else have questions?
Hi, Igor. This is Prudence. Thank you so much for your presentation. Just have a dummy question about one slide in your presentation, which is, so there's a one slide of 4 images of the knitting machine, right? To illustrate like how the knitting machine actually does the partial increase or decrease of the pattern. I know that that slide illustrates the, like, if I remember correctly, the method A, which is increase the knitting pattern. Before the method B, I think, which is to decrease some part of the pattern in, it's kind of hard for me to imagine like how the knitting machine actually need to work to go left and right so that I can finish I can realize the B method, if it makes sense.
Can you make your speaker louder?
Sorry.
Yeah.
So there is one slide showing like 4 images of the knitting machine to how to lift the partial increase pattern. But it's kind of hard for me to imagine like how the knitting machine does the partial decrease pattern. Well, I'm hoping if you can illustrate more and explain a bit more about that. Thank you so much.
Okay. So I'm now sending you Grasshopper first, and then I will answer to Prudence Yao. Okay. So you are asking like this one, right?
Exactly.
So from here, you can see there are 2 needle beds. So this is the number here represents the row number. So this is the first row. The knitting machine move from left to right, knit the front, and then knit the front needle bed, and then move to the second. So after knitting this row, it will drop off from the needle bed, and then the knitting machine move backwards and start to knit the next row here. It is connected to the previous one. So it will be a little bit hard for me to explain how these needles move. Which part are you actually, so how the machine operates, or can you be more specific? Specific, yeah.
Sure. So for the image B, if the knitting machine goes to the, let's say goes to the right to increase one more
Yeah.
width, if that's what it calls. So it will automatically increases the width, and that doesn't require any like human interference.
Like for this one?
For the second one.
For the second one. Okay. So for automatic machine, it has other. Can you explain that in English, Virginia? So
Yeah,
it has
so the CNC knitting machine is able to make all these types of stitches. So it's able to add stitches or remove stitches. If you use like a regular knitting machine, like the toy one that Yiga showed at the beginning, you could do all these stitches also by hand, editing them. But these types of stitches here, you would use in the program different colors to code in what type of stitches you need to make if you need to add a stitch or remove a stitch. Does that make sense? And the needles are able to shift from one side to the next or add stitches where needed.
Gotcha.
Yeah. So for automatic machine, like the needle bed can actually slide, so it doesn't need hands. It has double needle bed, and if knitting with transfer, the double needle bed can move this way. So like for this one, it can directly move one needle away and then move it to the place where it wants. So it has a lot of mechanism there to assist this different knit structure variation, like transfer you mentioned.
Gotcha. Okay, thank you.
I have a question, Iga. I lost when you're talking about Y and a special curve shape. You said it's like you have a program and explain and how to link them. And I was lost when you say, so it's not sufficient, only one line. I lost there. And why it's not sufficient?
So you can see from my approach, there's a continuous line here. So we can use one single yarn from the beginning to the end to knit the whole piece. But like for this one, you can look at the knitting pattern. You can see the row stop here. So it doesn't have a loop to go back. So the short row ends here. You have to do something manually. Because just for this fabric, you cannot using one single yarn to knit
okay.
continuously. And but I've talked to Mariana. She has improved this approach. I think this is just a simple demo, but maybe this paper is too early, so there are still technical problems here.
No, I mean and a dome. And a dome you show me, and so later you have to add much more yarn, or I forgot. I'm sorry, I'm not very good at
One?
this. Yes, or we go next. It's like around 27 or 26, and that part I was
Yes.
lost.
So this is just the stress analysis. To analysis its stress
Okay.
distribution. So
And
yes, of course. And when you are producing a fabric, like you are actually not using just one single yarn. There's combination of different yarns. Also, I said I add reinforcement onto this surface. So the yellow yarn has thicker thickness than the black one. So actually I'm using two kinds of yarns. But the very basic logic of knitting, it should be knitted by a single yarn. And then you can add complexity into that.
okay, I understand. Thank you.
And also here, I'm not criticized. This is really an important article to my research. Actually, my research is built on this method. So I follow this method and I find some problem maybe very important to me. So I improve a bit based on this method. And I also found she used a lot of increase and decrease. And I've tried this approach before, but like this piece is simple, so just one decrease in one row is okay. But when I add complexity to this geometry, there are several decrease or increase in this row. It is really hard to knit. I failed several times because I tested for different geometry. So then I just cancel this increase and decrease, just following the partial knitting logic to create the 3D geometry. Yeah, but this article really is if you want to develop your own method, you should read carefully about this. It will give you a lot of inspirations. So
I'm sorry, what's the name of the article?
Automatic. I can send you the name. Yeah. Yeah.
Thank you.
You're welcome. And I just sent you the model. Can you open that?
I just got it. Yeah.
Yeah, it may need some plugin from the Food for Rhino, like TT2 box and mesh curvature. I cannot send you this zip file. It says it's virus. You can download it from Food for Rhino. So make sure you install these two components first. Mesh curvature and TT toolbox. This one. Okay. So if you can open this file, you can find several geometries I already put in this file. I've classed them into developable surface. Like this one, it's a ruled surface lofted by two curves. And also these near developable surface, I call them, because they are not developable, but they can still be flattened by some method. And here is a more complex one. And here are the grasshopper file for them. Okay. I think I lost one. Okay. So the red part is flattened version of them. So in this class, we will not jump into the 3D method. We just start from the simple one that first flatten those 3D geometry onto the XY plane and then generate kneading code. You can see here the 2D pixel drawings based on this flattened surface. And you can play with it. Here is the geometry of this one. And you can link the mesh to this button. And this will compute a knit mesh. And also you have to pay attention to the knit size, typical knit dimension. I just give it a random number. This number should be calculated and measured from your samples because different knit structures have different knit widths and knit heights. So you have to calculate like within 10 centimeters, how many knits are there in one row and how many knits are there in height in column. So then you know the typical knit width and knit height and just input it there. It will turn into this pixel drawings. And also here, you can see, actually I just create parallel lines. You can change the number here because some drawings are fat, some drawings are thin. So if it doesn't cover the whole image, it just create half of it. So you can adjust the number here to make sure it covers all of your flattened surface. Okay. Here I also add the function of adding patterns. Here is a mesh curvature evaluation. So you can see there are different curvatures. I can extract some. I can extract areas with maybe it doesn't show very clearly. Mesh edges. I can extract those area with less curvature, and then it will be mapped onto the 2D. This is the main components is here. If you are interested, you can look at the codes here. It's a very basic ones. include all the, if you want me to explain it in detail, maybe, do you want? I'm afraid if I explain too early, you may get confused. And also for me, it's like written 1 week ago. So I'm actually, after 1 week, I cannot remember what I've written clearly. So you can play with it. You can input your geometries you created yesterday and try to input this mesh and to generate the knitting pattern here. And also you can, here I use mesh curvature. You can also add other analysis to this mesh. This is the value, so you just input a value and to your meshes, you can get whatever pattern you want. It can be structural performance analysis result or other things, and you can create your pattern here. I think, yeah. Do you have any question about this grasshopper file, or if you want to know more? I feel like the classroom is very quiet now.
Is everyone just overwhelmed?
Oh, really? Oh, I'm sorry.
I don't know. Are you?
So
exciting.
Oh, maybe I can introduce. So actually, the method I used to flatten here is the one that introduced by the Royal Danish Academy of Fine Arts. So they use. I also use this kangaroo. Use the flatten and on plane components. So the geometry here, I use the square of their differences, the length differences, to make sure the length is remain the same with the 3D geometry. The differences is only like at this level, so we can assume that the knit program based on this is similar to the 3D version. There are many ways of flattening one geometry. One is to make sure the length equals, one is to make sure the area equal, and the other is to make sure the angle between each line are equal. So I choose the one that to make sure the length of each mesh edge equal to the 3D geometry. This is the mesh, and this is the output. One challenge I left is that I didn't do the knitting optimization. So if I translate into the geometry, you can see it's almost symmetrical. But if you want to knit, as I mentioned, it should have a sneaky path. So if you are interested, maybe we can discuss how to make this pattern a knittable one. If you are not interested in coding, or maybe you will practice later, we can also do it on Photoshop directly to let you know how to optimize this knit joins, and then you can program it. Also, I would like to show you, after having this program, how do we export it into pixel drawings? So, like, first to export image, and it's better to keep the scale 1:1. Okay, let's do 2. Okay, it looks good. And then print it. Import it into the Photoshop and select the drawing you want to keep. Crop it. Oh no, sorry. Okay. And we can also, I forget to measure the length of it. So we have to make sure this is our drawings. We have to add a bounding box to that, so we know the dimension of its length and width. Okay. And then we can use this function. Can you see that? Alt Control I, yeah, and translate it into pixel drawings. Don't forget to choose this one. It's Alt 7. Yeah, and you can change it to, yeah. So it goes exactly the pixel numbers as the one showing this. Okay, so then we got the pixel drawings here. It doesn't have gradual variations. So this image can be imported into the knitting machine software. So can you give a try on the project you created yesterday, like adding your surface to this program to generate this knitting pattern? I think this is the task, and then we will go to the factory this afternoon to see if we can knit any sample. Is that clear?
Yeah.
I think maybe, yeah.
Yeah.
Great.
So everyone should have some Rhino models that they can start to apply these patterns to. They probably won't be so as complex. They should be kind of simple. So you can try.
Yes, if your model are very complicated, maybe you can divide it into different patches, so it can be computed easily. Okay, I will walk around to see how's it going.
We also still have, I can make some breakout rooms if the online students want to go into rooms with some of the in-person students or whichever for your team, because some of you may have made some changes or whichever for your designs. So I make 6 rooms.
Okay.
No, wait. Oh, okay, wait, hold on. I made them wrong. Cancel. I'm not that good at making breakout rooms, apparently. But yeah, maybe you want to meet with your teammates first. Does everyone remember what number room they were in yesterday for your teams? Okay. Okay. So you should be able to move to those rooms to check in with your teammates, to share your progress, because I know some of you have made some progress since last night, and then discuss which models you want to try to apply the material and work together. And Yiga will go around the room in person, and those of you on Teams online can meet with your teams in the room too.